Okay, before that, like I'll just try to give some basic announcements regarding the documentation. So we'll be documenting the whole video, presentation videos, and we'll be documenting the slides, annotated papers, and code bases. Right. So I'll be like, this is my GitHub account. So like I have created a repo. It's a public repo. I'll be sharing this soon in the group. Then I'll be like just creating 3 folders called slides, codes, and annotated papers. You need to fork this repository in your account and push it and create a pull request. Then I can merge it into like a full account. We'll keep this for now as a public. Then when the semester ends, we'll make it private and like we'll see whether you can share it with the juniors or like something. So we were like having 2 options. Either first we'll start with GitHub, then we'll be having some activities in the GitHub as well. People can get some things on GitHub. If it doesn't work, because like GitHub has some constraints of 2 GB cloud storage, and we cannot push up more than 19 MB of data in single push. So those things are there. We can use Git other thing, but for now we'll stick with Git. If it expands, if it goes more, we'll stick with Google Drive. So for that, that's it. So I'll start my presentation. Okay, so I'll be sharing like this will be the unit. So this will be like kind of a 80-20 percentage technical and some other things. So we know what day is today. So we'll be like discussing, like I'll be like going through narrating through a love story of a which gave like a which opened new domains in the AI features. So when love is bound by skip connections, the unit romance. So for that, okay. So we'll start. So where it began was the tale of the blurry boundaries. So initially, the need for a segment, like the need for this approach to have a segmentation. So initially, example, so we know about what is semantic segmentation means. We'll be having 3 channels, RGB channels, and we'll be like creating the pixel-wise labels for these channels. So the semantic segmentation was done from the beginning, it was done in various aspects using FCNs and CNNs, using mini receptive fields, and so on. But the real problem arose when we are moving to medical images. So in medical images, the first we will be finding is the number of data. So there will be lack of data, not like the real world images, we cannot get the data. So collecting the data will be expensive and there will be lack of data. And another thing is the medical images are prone for deformations like the shift and rotational invariance. So we should have a robust pipeline to capture this invariance. So at 2015, the Ronneberger introduced the paper unit for medical image segmentation. But the unit was stopping only with the medical image segmentation. It extends its route for segmentation. As I mentioned, you will be seeing this unit, right? So now it extended for super resolution. If you see super resolution, we'll be having the same unit. If we go for diffusion, for image generation, diffusion. For diffusion also, you'll be saying the same unit. So unit extended its roots for various domains. So this is the importance of the unit paper. Okay. So starting along with like existing architectures with FCN, so like fully connectedness and convolutional neural networks. What had happened is they'll be having the same image, they'll be having
fully convolutional networks. FCNs.
Yeah, in FCN, yes. So what happened is, so they'll be having a CNN with like a kernel function. They'll be having a sliding window mechanism to slide through the image pixels to construct the high-level feature maps of the image. So usually they'll be having the high-level feature maps. As the network goes deeper, they can localize the information, but yet slow. Because like they'll be like sliding the kernel along the images. And also there'll be another problem. We'll be capturing the redundant information, right? And there will be like a trade-off between the localization accuracy and use of the context. So example, like if we have like a small window here, we'll be having less context information but high localization accuracy. If we have like a high window, we'll be having more context information but less localization accuracy. So there was the trade-off between these things. And also like there were some already available model variations like utilizing skip connections by Sami, getting the connection like as we like what happened in present day. But these were not up to the expected levels. So in 2015 for the ISBI challenge, so in that challenge only, this like medical image segmentation challenge. So there only they have included this unit architecture. So let's go to the unit story. So comparing to the unit story, we'll be like introducing our lovebirds, Mr. Encoder, and we'll be having our other protagonist, Mr. Decoder. Right? So they were fully functional, and they were even though they were separated, they were like fully functional. They were doing their work, but they were not up to their optimum level. So they need something interaction between. So they introduced skip connections. Okay. So moving on. So what happened with the unit was, so this is the architectural page of the unit. So as you can see, like the U shape of the unit. So here we'll be having first one, the decoder part. So encoder part, they are mentioning it as the contracting part. So in this contracting part, you just like see a double convolution, and I will explain that in a while. Convolution, pooling. So here what will be a thing? What is learned from the image? So the context information has been learned from the image. What is learned from the image? Like they'll be having sequence and pooling. Moving on to the decoder, we'll be having expanding path. So this will be the decoder. So decoder decodes what where is in the image. Ronneberger is where is in the image. Sorry for that. So here what is learned from the image, and decoder will be like saying from where. So it learns a localized concept of the image. So that's the decoder and encoder paths basic architecture works. So in encoder will be having CNNs and max pool layers. So so it will be like a downsampling path. In expanding path we'll be having transpose convolutions and CNNs as like upsampling options. So if you are like talking about the encoder, so with the encoder we'll be having with the encoder we'll be having so as I mentioned earlier, the encoder learns the contextual information like what is in the image, and generally gradually generate the hierarchical features at different resolutions. So we'll be having different pooling at different resolutions, so extract the generative features. It also consists the double valid convolution followed by ReLU and a 2x2 max pool sampling. So I'll just explain the in a high level way. So as you can see, like you can see the image dimension. So 572, 570, 568. So these are like just using 3x3 valid convolutions. Valid convolutions mean no padding. So they'll be having those things, and then they'll be having just like a max pool to reduce the dimension and increase the channel size. So this will be like a kind of a double convolution followed by ReLU and followed by a max pool. So this is like the whole encoder path algorithm. So if you see, I have like explained the codes as well. I'll be just going through in a while, but these will be the codes I have included, starting with the starting the double convolution class. So I'll be starting with the convolution 2D convolution. So the best normalization, one thing. So I have like done some modifications in the code. First things, when the paper came into the world, best normalization was not released. So the best normalization was released after this paper. So I included the best normalization, and I included the and also like rather than using valid convolutions, I use the same convolution, like having some padding features to like just mitigate the input output image size variance. And then after that the best norm and the same thing. So we'll be having a convolution which will be like the double convolution followed by the pooling layer. So that will be the downsampling path. And if you can see, as like in the, so this is like the like a architectural abstract architecture of the class. So as you can see, like I have like encoded with the channel number. So you can see from the channel starting from 1. So it's 1 if it's a grayscale. If it's RGB, it will be having three channels starting from 64, 128, 256, 512. And you can see like starting from in channels, I will be expanding for same thing 64, 128, 256 and 512. So that's like the for the encoding part, which is like what learns the contextual information in the image. Going for the decoder. So in decoder, learns the localized information. Where is in the image? That's what's learned by the decoder. So it's exactly upsampled the encoded part from the the details which are encoded by the encoder to the output resolution. So as you can see, we'll be seeing due to skip connections, there will be a large number of feature channels comparing to the encoder. So this large number of feature channels allow network to propagate the whole features encoded by the encoder back to the original image resolution. So here we will be having 2 by 2 transpose convolutions. You know how the two transpose convolutions work. It's like opposite. In convolution, we will like just shrinking the image size. In transpose convolution, we will like extending the path. And then after that, same 3 by 3 valid double convolution followed by redo. This is like the basic architecture of the decoder part. So the decoder. So this is the decoder part. As you can see, like we'll be having initially we'll be having only 256, but comparing to encoder part, we'll be having some additional channels. I'll be explaining in a while why these channels are important. And these additional channels will be like propagated through the whole pipeline. And here also you can see we'll be extending the image variances, like image sizes, using transpose convolutions, and then we'll be like following up double convolutions. Okay, so this is like the code for that. So as you can see, like we'll be having the same converse, like transpose, like the transpose convolution and the double convolution as I explained in the previous one. And for this, I have like just like parallel. For usually what happened, like I'll be like explaining in a while in a thing. So there'll be some concatenation connection from encoder to decoder. So in the original image, as they are using valid convolutions, they just crop and replace. In my implementation, I just pad it using some like getting the size differences and just like pad. So I think normally we don't need, because as I am using the same convolution, we don't need this, but in case I just use that. And expanding from the, like I'll be just concatenating the x1 and x2 and x1 features. So upsampling part also, starting from 1024 channels, I'll be moving back to 64, and after 64 I'll be like, just here they have like went to 2 channels, but it's not necessary to be 2 channels. We can have as many channels as much as label we can. So here I have done a binary segmentation, so I have to just stick with 1 channel. Okay, so coming back to our story. So here the encode, like as a love starts, so as the relationship starts, there should be a promise to be done. So the encoder made a promise, he would be a better half. Right? But he's not that he's done. He did. So what he did was he gave his half part to the decoder. To make it like, to make her like fulfill, like to enhance the performance, he just gave his like whole 512 part to the decoder part. So where he will be like, we'll be just explaining where it's important is, it will be like skip, like it will be propagating the high resolution features from the encoder to the decoder to extract the exact pixel location of the segmentation marks. So
what you're saying is, rather than using the cropped version, you padded, right?
Yeah, I padded. But in the original paper, they have just cropped the version. So why they cropped this? They were using valid convolutions. I'm using same convolution. That means just padding and just like adding. So high resolution features from contracting path are concatenated with the upsample input, and they will be propagating the contextual information from the encoder through the decoder path. So that's why they were able to get the enhanced output of the images. So even though the downsampling reduces the spatial information, skip connections pass high resolution features directly to the corresponding decoder layers, which helps to recover the lack of details and detail accuracy. Moving back, so now our decoder is first example. So this is how it happens. So example, the decoder will be decoding, okay, this area will contain a byte, and encoder will concode, okay, these pixels will contain a byte, but you don't know where the location is. So when after having the skip connections, where we are having the both features, we'll be having the combined features, and from the combined features, we'll be able to show, okay, this is the exact location of the mask. This is the exact location of the mask. So this is the overall architectural idea of skip connections. So with the skip connections, our encoder is now, decoder is happy. So no matter how you deep to contract, I know will you bring back every lost detail for me. So that's what they do. So that's what like a cute a story from okay. So they extended their implementations on many aspects. So this is going back to the training. So we'll be having so example is saying so this unit has been specially trained on less number of data and using this for strong augmentation because as I mentioned, medical images are prone for deformations and we need to learn like a deformation invariant model and also there's only small number of data so that they'll be like learning more efficient details and they'll be having slight output input image change size change because due to the value convolutions it won't happen in my demonstration, it will be like in same and they'll be having high momentum. So as you know, everyone knows high momentum. What is momentum? So momentum will be like getting the knowing the features from the existing past gradient. So here they'll be having high momentum. So they are mentioned as 0.99. So as they using high momentum, they can learn from the ancestors like the past gradients. Also, when the paper was rising, that was the golden era of GPU computing. So still the GPUs were on less in memory. So to use the maximum use of the GPU, rather than having many batch sizes, they reduce the batch size and increase the tile size. So in that case, like they can use many contextual information, right? Rather than storing only small contextual information for many images, they took only small some of the images and stored many contextual images, which helped them to overpass the existing architectures. And in the last part, they'll be using the softmax functions. So you know the softmax function, what happens? So the softmax functions and the cross entropy loss, after loss, and the softmax function and the final activation layer, which change the logics into a more accurate probabilistic distributions. And also here, like there was an interesting way. Unit not only segmented, they were able to segment the conjoined boundary parts as well. So here, how they do is they created a weighted loss. They created a weighted loss map. So as you can see, like this is the output of this weight map loss. In the boundary part, you can see there's like some deviations with the as you can see like there's like some red and like blue patches in the boundary. So what they do is they'll be assigning the weights like they'll be assigning high weights for these boundaries. So how these weight boundaries are being calculated using these morphological operations. They are mentioned these as morphological operations. So he'll be like using D1 as like from the image point to the one boundary of the cell and D2 as another boundary of the cell. So there's like just a basic morphological operation. So from that they'll be able to create the like a whole weighted loss for exacting the boundaries of the cells. And they'll be using key initialization. Key initialization means like to initialize the model weights. So according to the number of input features and number of channels, we'll be including like getting a Gaussian distribution according to that, and with the Gaussian distribution, they'll be assigning the weights. So that's the concept of relation. So example, like if we have 3x3 channels and 64 like 3x3 kernel and 64 channel, we'll be having 3x3 into 64. That will be the something. So with respect to that, they'll be having a variance comparing to like with respect to that value they'll be computing a variance, and according to the variance they'll be computing they'll be sampling from the Gaussian distribution to initialize the weights. Okay, now we can move to the code implementations. Just explain. I hope my screen is visible. So you can see it's my so as I mentioned, so we'll be having with con 2D. We'll be starting with starting with the like encoder part. So I have created in the face of like unit parts and comparing the unit. So in unit part we'll be like storing the abstract information about how the unit part should be, and using the abstract we'll be like defining the concrete implementations on the unit, and then we'll be having a main code and inference code to see the how the outputs are coming. So moving on, so he'll be having a convolutional like con 2D with 3x3 kernel size and one padding, and I'm having bias false. Why I am using this bias as false is I am using batch normalization. So assuming you need what happens in batch normalization, we'll be having the weights, so wx plus b, and we'll be deducting that with the sum another wx plus b. So that plus b minus b cancels out. So we don't need that bias part. Am I clear? So like Wx plus b, so we'll be like in batch normalization we'll be having like yc1 minus yc2 over the sigma. So that's how the batch normalization get computed. So anonymously the b bias part will get cancelled out. So we don't need to calculate the bias. So I just make the bias as false. And the ReLU, and as I mentioned, the batch norm was not introduced at the point of the paper. I just introduced in sake of. And again the convolutional 2D, the ReLU functions, and as like a downsampling part, I'll be having a double convolution and a max pool. And for the upsampling part, I'll be having the converse convolution, like transpose convolution, and the double convolution. Double convolution will be having only the convolution and.
Also, did they use transpose convolution?
Yeah, transpose convolutions. So these like, transpose convolutions are like the same. These implementations are the same. Only the things I have included, changed is having this as padded one and batch normalization. And also like this was also like not needed. So I just like got it from how they might. I just like get how might they cropped it. Like just like they get the calculation from the x2 size, like from the concatenating size from the from the encoder size to decoder size, and I just like pad it, but we don't need that. We can just concatenate x1 and x2. If I check like the dimensions will be same. Okay, moving on to the then it's like moving on to the unit. Okay, for the unit, so we'll be
the implementation, the center cropping was what they did.
Yeah, center cropping. Yeah. So here in the unit implementation, we'll be having, as I said, from in channels. So I have like demonstrated these classes, these abstract classes in the unit parts. So I just like using the in channels, making it to 64 channels, 64 to 128, 128 to 512, all the way to 1024. This will be the bottleneck layer. In bottleneck layer also, like they will be having the double convolution, like a convolution, then padding. So you can see the paper. After that, I'll be having the upsampling. In upsampling, I have defined both the upsampling part as well as the concatenating part, as I did in the fourth function. So I'll be like getting those things, and yeah. So in the fourth path, I'll be having the down convolution, and in the upsampling part, we'll be having. So in the down convolution, we'll be having two things: the down sampling and the pad part. We actually get padded. And in the upsampling one, we'll be having the bottleneck and the downsampled, like where it will be getting from the paths. So at the out we'll be having the upsampled one. We can like move into the. So for that here, rather than using medical images for simplicity, I used an image called like a image data set called Caruana dataset. So this is like a famous challenge in Kaggle. So this is like we got it from Kaggle. So this is like just getting the car images, just getting the car images. So this is like just basic implementation of getting that using data loaders. So I can show some images of that car dataset. These are just car images, and I'm just segmenting the car and going for the training. So these are my hyperparameters. Like I just like a truth of whole, like having 3 to the power 3 to 10 to the power minus 4 my learning rate, and the reduced batch size. And I just like for now I just like train for 3 epochs, but you can like learn for many epochs, as you know. But for my case, like even with 3 epochs we were able to like get high accuracy, like around 98%. And that's it. So the basic training algorithm where I will be getting the image and mask.
Accuracy is measured the pixel wise.
Pixel wise. So in the original paper they have mentioned IOU, intersection of union. So as they are working on medical images, so in their work they having attained like a mini, like comparing the previous work, they are having around 8 to 10% of accuracy improvement. So as I like sticking with only with the thing, I just like mention the pixel wise accuracy. And also you need to mention one thing in the final, maybe in the unit. Like one small sample. Okay, so I cannot remember where I put that. So what I did was, so I just did they were using softmax functions, but I used, as I doing with binary classification, I just used sigmoid. So softmax and sigmoid are both are like somewhat same, like in terms like, if I can explain, if I write, will it be visible to you?
I don't think the writing will be recorded.
Yes, sir.
Writing will be recorded.
So like
Just
You can actually use
Zoom writing.
Zoom, sir.
Zoom writing. Zoom writing.
where is that?
Touch on the screen, sir. Can you see that annotation?
Okay, so like here we can see what has, so example for two classes, if we see the softmax e to the power z over e to the power z1 plus e to the power z2. So if we like divide this, like if we multiply this by e to the power minus z1, 1 over 1 plus e to the power minus z1 minus z2. So in case like if we make this as z, then it will be just like a 1 over 1 plus minus, it is segment function. So mathematically it's okay, fine. So I just like did that one small augmentation. And okay, coming back. Then the same thing, like the same training and validation. So I can like just like show that thing happening. Okay, now you can see like the model is training now. So you can see like the training phase, it will take around 2 minutes, like altogether 6 minutes, but I have already got the training done and I have saved the model and I have got the inference. So inference also, like I have just use the same model, got the model and just like created the predictor class and save it as like single image inferences. So that's what we did. So it's more or less same as the validation part. So I have like got 6 images. I'll be showing the original data and the masking data, like got the image. So these are the images, as you can see. This is like a Carvana image. Okay. So this is like just like the car samples, and for this I'll be having the masks of this one. This is like these are the training masks for that image. So what I did was I ran the output, and these were the saved predictions for the input classes. So you can see. So this was like the original image. So I had just like transformed that image into 512 into 512 to reduce the model complexity. And this is the original image, and this is the predicted output. So here like you can see some disaccuracies, like here the wheel part, and then like one small this part is not getting like perfectly masked. Some some deformations are there, but more or less altogether we can have like have a comparable accuracy comparing to the original papers. So this is like just simple implementation of unit for one instance for segmentation, but it has like been many avenues for even for dollies and other stuff were created using it. So I use like the decoder and encoder one from ChatGPT, so it's also from the same unit architecture. Okay, so moving on with code implementation we have done. So I just need to cover a small part on trans unit as well. So you know like what's happened in unit, but unit were having some constraints. One thing is like even though they are having like high localized information, like high information, even though they are CNNs, they won't be having, comparing to the transformer, they won't be having that much global contextual information. So the transformers, they will be having much more global contextual information than CNNs. So this was adapted from vision after the introduction of vision transformers. So they just got the vision transformer. So what they did was, still even though vision transform is there, they'll be having the image patches and they'll be converting into images. Still the localization problem was there. Even though they are having the contextual information, they need much more. That worked in the ablation, they said that worked with the previous one, but they need more high information. So that's what they moved with hybrid architecture with CNNs and VITs. So in CNNs we'll be having the high level contextual information, just like getting the image, making into tiles and just like learning through the CNNs. And after the CNNs, we'll be having a linear prediction layer, which will be predicting the whole CNN features to a d-dimensional embedding space. And from that embedding space, they will be having the position encoding, and that will be encoded, will be given to the transformer layer. And from the transformer layer, we'll be having the embedding plus having the most known way of the transformer work, self-attention. So with the attention, they'll be able to get the more complex global information. Using the CNNs, they were able to capture the high level information, low level, like in many hierarchical levels of information. So after that, the same decoder part. So decoder part also like more or less same, right? So where this and the skip connection idea is also same. Rather than getting from the hidden features, they'll be getting the features from the CNNs output. So like the same what they did in the unit, they did the board. So in the ablation study, they have started with like having just only VITs without any skip connections. What is the output? Then with the VITs, with the skip connections, what the output? Then with the skip connections, only VITs, what the output? With the skip connection, only CNNs, what the output? Then combine, what the output? So just like that, they have done the way, and with the way, they were able to like have a more comparable performance than unit. So that's like a small insight, but TransUnit is not only in conference.
It has not been published.
It's just like a
Process of citations.
Yeah.
We also use that for our liver segmentation work. Very nice.
Yeah.
Very nice.
So one thing like they were mentioning is like this the CNNs, like the unit, they had some even though they have a deformation invariant, they had some problems in segmenting small pieces. Like in case like you can see like the small tiny blue dot. In that case, like I can. I don't know, like, but just like. No, I just said, but I was not able to understand.
All the out of the world things he does transformers, this, that, and so on, but he doesn't know what the token is. I also don't know. All these out of this world things he does. Inside the body, the organs, he doesn't know. Who is a biomedical person in this?
Okay. So this is what happened. So like this, like so in this, like this is like the unit, and you can see like with the.
It's there.
Okay, then
This is there at the top.
I think. Yeah. I think the iota. Okay. So they were mentioning about the kidney. These things. So these are like these blue and blue, right? This is like left kidney and like right kidney. They were not gathered like segmented by the unit. So like here I think like the spleen will get jumped into this thing. So but those things were there. So they're having this under segment and over segment problem. So comparing to the unit, and this is also they have done using this is what I have mentioned. So comparing the unit, they have introduced one thing called R50 VIT cup. So R50 means instead of that CNN, they have included the R50 like Resonate 50 backbone, and with the same VIT, and then without skip connections. What's happening? So that was the initial work, and along with that, then only they have converted to TransUnit with the skip connection. So comparing to all these things, TransUnit performs well. Yeah. So that's it with the TransUnit. I think that's it with my presentation. Any questions?
Any questions, Vishagar?
I think measure what's skipped on the main part and how does it affect the performance of that? How, like you measure what they are getting a half of information from the encoder-decoder, and how to decide which part is.
Okay, so encoders, like as I mentioned, encoder will definitely learn the context information. That's a byte here, right? So it definitely not. But encoder doesn't encode the localized information where it was there. In the decoder part, it knows, okay, this area will have a byte, but exactly don't know which pixel exactly is there. So this skip connection enabled the pathway to get the features from the encoder. Like these pixels will have the how to say, there's a byte in this area, and the decoder will say, okay, this is definitely in this area, With this combining those features, we'll be able to get we'll be able to propagate the high resolution features from the encoder to decoder to get the output. So we'll be having like more robust, what to say, very good segmentation mask, like the more accurate segmentation mask comparing the existing ones. Like with the old plus, in simple words, the segmentation mask with more accurate contextual and localized information.
So in the paper, like it is talked about using momentum. So what role does it play when the batch size is really small?
So as I'm like that's also like one thing. So as I mentioned, the GPUs.
What's the website actually?
Here. I just use yeah, very small. Yeah. So the main problem in the thing, like first the GPU computation is just very slow. I think they have just only 6 GPUs of GPU. So what they were arguing is, rather than storing many small information, they can store some large information in context. So in that case, what they did was they just reduce the batch size and increase the tile size to learn more contextual information. Plus, as they're using many batch size, even though there were no any batch normalization or no any normalization things with that. So for their an optimized performance, they have this high momentum. So what momentum does is it will propagate the gradient information from the previous backpropagation inputs. Right? So if we have like a high momentum, we'll be having a high proportion of the gradient from the previous training. So we'll be like propagating those information to the new one will be like contributing more to the an optimized way of convergence.
You mentioned the tiles. There's a tiling mechanism also, right? Because the image is large. You have to select a larger area than what is interested and then tile it, right?
So they are like they have this like got on the
you cannot see it. Participation marks.
It's like they are having this 572 by 572 files. So that's what they. So in the image, like there was some other implementation, like as I need to show. I hope it's not relevant to this paper. I think it's from the original paper. This one they mentioned something like. Okay, this is. But they haven't mentioned about this thing in the paper. So what they did is like this. Like I hope this is like a previous way. It's like overlap tile strategy. So this overlap tile strategy is like this described by some other people.
Okay. It's not their contribution.
Yeah. Not their contribution. It's like an existing architecture. So what they did was okay. This is like the existing thing. So here we need to get this segmentation out. This segmentation out. For this, they'll be having this all blue part context. So to get the segmentation of this one, they'll be using the whole blue part context. So prediction of the segmentation in the yellow area requires image data within the blue area is input. Missing input data is extrapolated by mirroring. So they'll be like just mirroring and they're getting the input. So this is like from the previous implementation, what they did. But here they are not doing anything. They're just like resizing the clock into 512 and just implement that. In my case, for the Karmana, I just like resized it to 512 into 512 each batch. So like originally it's like a high resolution image with 1000.192.0.10.524. This is sample into 525. So if we have more computation, we can have a high resolution images.
Okay, any other questions?
Small question. So like so the thing, the question I got is what happens if we add the output from the encoder to the decoder's like output instead of concatenating it. What will be the results? Do we know about that or like?
That is summing up.
Yeah, summing up like in transformers. It's just an idea, so if you don't know, it's fine.
Okay.
No, I was also thinking
Okay. But their argument is like they need high feature maps to be decoded from the decoder bar. That's why they were able to get more accurate information from the decoder propagated through the decoder. If we have that reduced, like just using the same number of channels, I think we can do, but comparing to the original paper, we might lose some localized information.
Yeah, so as you mentioned, the encoder is doing one thing and the decoder is
another thing.
Yeah, I got it.
So exactly saying like this is what they mentioned. So there will be like large number of feature channels in the expanded bar. So this allows network to propagate context information to the higher resolution layer. So with that only they will be able to like get like more information which can be propagated into like a higher resolution. If you have like less number of feature information, then it can propagate comparing to the previous one, it will be less.
Yeah, so just out of curiosity, I wanted to know why you use double convolution specifically, because when you look at convolutional like CNNs, the Lumen, all those architectures, they use the convolution operation and pooling, convolution pooling, and that's the pattern, right? But here, double convolution and then pooling. Is there a reason why double convolution, why not triple convolution? Just out of curiosity.
Okay. Exactly, I haven't tried that. Maybe if I get some, it may increase the performance. We need like compare with the like whole data set to try and test with what happens. But it can be done like they have just done as a working model. We can expand that. If we have like now we have like more computation, we have 24 GB of thinking, we can like have a Resnet 54. So that's what happened in TransUnit. For TransUnit, for the ablation, they just did that. They replaced the encoder by Resnet 50. They will perform well than unit, but comparing to the TransUnit, they didn't perform. Chaining the encoder with Resnet, it worked.
After 3 convolutions, they have pooling, right?
Yeah.
Convolution, 3 convolutions.
That's a convolutional block in Resnet.
Yeah.
The question you asked. This one, so they'll be having this like VNet and dart or something, but they're having this like same unit with R50, Resnet 50. And comparing the original thing, they're having like high mass like DAC and half-stroke distance values for Resnet 50. So this is the ablation they have done. So chaining the same unit and having the Resnet 50 as encode, and moving to the transformers, we'll be having the same VIT with no skip connections and having the skip connection. And with the same skip connection, they'll be having VIT plus VIT plus Resnet 50. Like for a fair comparison. Then they came to the TransUnit. So TransUnit will be having the skip connection plus high level convolution like hybrid CNN plus transform architecture. That's it. That's it.
Okay, then we thank Vishagar for the excellent presentation. Very appropriate presentation for the Valentine's Day.
Like,
At least the presentation is there.